All right, we've moved on to page 3 of lesson 2, and here we're going to be discussing the multiplication rule. And while we're doing that, we are going to encounter tree diagrams and independent events. Let me just say a word about tree diagrams before we begin. Many students find tree diagrams, as with the Venn diagrams, to be just a little bit of a challenge to get started. It turns out that these are some of the most helpful tools we have when we start working with probabilities. Tree diagrams in particular will help us to solve some problems that are really quite difficult to solve without them. So this is something we really do want to focus on carefully. We're going to start with a couple of classic examples that show us the difference between independent and dependent events, and it'll also give us a chance to start working with tree diagrams. So in our first experiment, a coin is going to be flipped, and on the first flip we're either going to get a head or a tail. When we're working with our tree diagrams, we're not just going to call that H or T, we'll call it H1 or T1, meaning a head on the first flip and a tail on the first flip. According to whether the first flip is a head or a tail, then the coin is flipped a second time, and once again you'll get a head or a tail, but we'll append a 2 on there so we can tell whether that occurred on the first or the second time. So how many possible outcomes are there? That's not hard to solve either by direct counting or by a tree diagram. Let's take a look at direct counting first. Now, in the past, we've usually just labeled these as HH for head on the first, head on the second, head on the first, tail on the second as well. You could use subscripts, or you could write this out as we recommended above. You could say H1, T2, H1, H2, and etc. List all those out, but the point is, especially when we're drawing our diagrams, we want to be able to distinguish between whether that head occurred on the first or the second flip. Well, right there we've listed all the possibilities. It's very clear there are exactly 4 of these. Yet another way of thinking about this is the multiplication rule, where we would say, well, how many options do we have on the first step of our experiment? Well, 2. There could be a head or a tail. Similarly, for the second, 2 times 2, there are 4 possibilities. Now, a tree diagram will allow us to think of this in a step-by-step way. Sometimes this follows exactly with a physical situation. Sometimes it's more of a logical way of breaking down what's happening. But in this case, it's actually physical. We're going to flip the coin twice. So the idea is you have some starting point, and then you flip the coin, you're going to either get a head or a tail. Now, once in a while you could get away with just that, but I'm going to call this H1, meaning I got a head on the first flip, and T1, meaning I got a tail on the first flip. Having flipped the coin once and having gotten a head on the first flip, I'm then going to flip again. And 2 possibilities occur. You could get a head on the second, or you could get a tail on the second, and of course, exactly the same thing happens if you got a tail on the first flip. Now, with a tree diagram, the possible ways for the experiment to terminate are indicated by what we call here, this whole structure is called the tree. These individual places where a line either starts or terminates is called a node, and these nodes, which you end up with that don't go to another node, those are called sometimes terminal nodes, could also be called the leaves of the tree. Kind of a cutesy name, maybe a little too cutesy, but nevertheless, that's what people say. So these leaves, by counting these leaves, we see how many possible ways the experiment could end up. There are 4 possible ways, and you read them off like this: a head on the first, followed by a head on the second, a head on the first followed by a tail on the second, a tail on the first followed by a head on the second, and a tail on the first followed by a tail on the second. So no matter how you do this, whether you just list all the possibilities in a list, whether you use the multiplication rule, or whether you draw a tree diagram, you will see that there are exactly 4 ways that this experiment could come out. Now the question is, what is the probability of getting 2 heads? Well, the probability of getting 2 heads is, there's only one way of getting that. In the tree diagram, that would mean we landed here. We got a head on the first flip and a head on the second flip. Now, we're used to doing it this way, where we say these are equally likely outcomes. Of the 4 possible outcomes, exactly one of them, so a pair of heads, there's exactly one of the 4 possible outcomes that gives us a head followed by a head. If you wanted to be a little bit more clear, you could use some subscripts, or you could write them up on the same line as that. Wouldn't really matter. But the probability of 2 heads, flipping the coin twice, is 1/4. Let me show you how that's done with a tree diagram. What we do is we first ask the question, and this is the beauty of the tree diagram. It allows us to think of our experiment, the outcomes of our experiment, a step at a time. So let's suppose we're flipping the coin for the first time. What's the probability that we get a head the first time we flip it? Well, the answer, of course, is 1/2, and the same would be the answer for tails. Now let's suppose that we did in fact get a head on the first flip, and now we're going to flip again. What's the probability of getting a head on the second if we got a head on the first? Well, of course, the coin can't remember that it came up heads last time, so this will also be 1/2. As a matter of fact, everywhere in this experiment, every time you're going to flip the coin, there's a probability of 1/2 of getting a head or a tail. You should notice this though. 1/2 plus 1/2 is 1. That sums to 1 because on the first step there's exactly 2 ways for this to come out, and therefore the probabilities of each of those 2 options should sum up to 1. Same thing happens here. 1/2 and 1/2 are 1. Same thing happens here. Now if we multiply the probabilities along a particular path, so by path I mean a way of landing on a leaf or a terminal node. Head 1 followed by head 2 has a probability of 1/2 times 1/2, and that is 1/4, which of course agrees with the way that we did it before. So whether you're doing it with a tree diagram or whether you're doing it by direct counting, the probability of getting 2 heads is 1/4. What's the probability of getting 1 head and 1 tail? Well, if we were to do that by direct counting, we'd say, well, there are 2 of the 4 outcomes. Of those 4 outcomes, exactly 2 of them qualify. So the probability of getting exactly 1 head and 1 tail, both, is equal to 1/2. In our diagram, we can see that as well. The ways to get 1 head and 1 tail are these. Number 1, you could get a head on the first flip, followed by a tail on the second. That one has probability 1/4. The other possibility would be to get a tail on the first and a head on the second. That one, 1/2 times 1/2, once again, 1/4. So the ways of getting 1 head and 1 tail are head first, tail second, tail first, head second. Sum those up because they are mutually exclusive. We have 1/4 plus 1/4. 2/4 or 1/2 is the probability of getting exactly 1 head and 1 tail. You can get that from the tree diagram. You can get that from counting.